Dimitri Ktenas, and I'm the head of the Wireless Technology Department at IIT, located in Grenoble in southeast of France. And so LETI is belonging to CA, and LETI is the Electronics and Technology Information Institute, and it's a research and technological organization regrouping 1,700 researchers here in Grenoble. So I'm here today to speak about the French Priority Research Program and equipments for the networks of the future, and I will give you some, let's say, high-level overview of what is ongoing on this program. High-level positioning of the PEPR. So just to understand. The general framework of this program is coming from the French Ministry of Economy, Finances, and Industry and Digital Sovereignty. Actually, the French government decided to start in July 2021 a French National Acceleration Strategy on 5G and beyond and future network technologies. And so the French government decided to work on 4 components within this national acceleration strategy on 5G and beyond. First component was the demand components in order to contribute to the competitiveness of the economy by developing 5G uses for the benefit of territories and industry. The second component of this acceleration strategy was related to the sovereignty. So the idea was to establish a sovereign offer on telecom network. The third part is related to R&D component, whose goal is to support very high-level French R&D and future network. And actually, the PEPR is the instrument to answer to this R&D and component. And there is also in the strategy a fourth component, which is education component. In that sense, the idea is to strengthen the education offer on future telecom networks. So the PEPR, this is this axis 3 here, and it works actually within this acceleration strategy together with the offer component and the education component. We were asked actually by the French government to think about a specific vision, to give a vision of what should be this program related to the networks of the future. So here you have, so of course, the first component is, this part is related to the increase of capacity to reduce the latency and to increase the number of connected devices. This is the first part, but more important is to make a convergence between the vertical sectors in order to bring a new phase of digital transformation. And this includes Industry 4.0, this includes transportation, this includes energy, health, and health. So this is about the service and let's say the KPIs, but there are also physical components, of course. So one axis is to work on non-terrestrial networks, and in order to move from 2D connectivity to 3D connectivity. Another important aspect is to merge the connectivity with the physical space, and this is done in particular thanks to reconfigurable intelligent surfaces. Another aspect is related to the usage of spectrum, and this includes actually the optimal use of spectrum and moving towards sub-terahertz and terahertz communication. Then the third component is related to the networks itself. So in that case, we try to move to a new architectural paradigms, including the convergence between network, cloud, and sensing, and also more classical things such as virtualization and slicing, in order to make kind of a smart orchestration based on AI control for end-to-end resources. We also tackle of course, the end-to-end security mechanisms by design in a multi-stakeholder context. And last but not least, an important aspect that we want to tackle is the sobriety, which means sobriety in the consumption of resources, and also in order to reduce the electromagnetic wave field exposure. And also in these resources and usage, we want also to address the acceptability of citizens and to think about, from the economy standpoint, to think about new use cases and new business models. So once we settle the vision, we structure then the program around layers and we structure it around a project. So here you have the different components that we wanted to tackle. So first part of the system, you have the hardware components for telecommunications, for instance, antennas, power amplifiers, and so on. Then you have the physical layer. So this includes, of course, the radio part, but it also includes the optical part, and this includes technologies. For instance, beamforming aspects, RIS, but it also includes signal processing and information theory. Then when we move to upper layers, you have the network architectures and infrastructures, and then on top of that, you have the service architectures and infrastructures. You have also, as I said, the resource sobriety across all the layers, and we have also a deeper look insight on fundamentals limits of the performance of the systems. And on the columns here, you have the different let's say verticals that are tackled. So we spoke about industry 4.0, but you have also energy with smart grids. You have also connected vehicles, and then we move to multi-sectoral federation, meaning that we aggregate different verticals, for instance, connected vehicles and smart grids. So one project is dealing actually with one or more lines, so here, but also with several columns, and this will be explained about the project itself. So we got our mission statements from the government in the end of September in 2021, months after the launch of the national systems. Then we only got 2 months to 2 months and a half to submit the full proposals of the project, so it was quite hard actually. And then there were several iterations between us and the government in order to make this program validated in February 2020. And then we started the project actually at the beginning of May last year. So we have 10 ongoing targeted projects with a total amount of 14 million euros. And there are also a call for projects. So about the project, we had some clustering. So first cluster is related to networks and service architectures, dealing with first project with architecture and the other one is architecture and networks. We have then another cluster related to technology building blocks with this one project related to self-res subject related to millimeter wire frequencies, so from 100 gigahertz up to 300. Then we have end-to-end system and uses. One project related to IoT and industrial IoT, making the link with the verticals. One project related to energy sobriety, one project related to security, one project related to fundamental. And above all, we have one project related to experiments and demonstrators. And the idea is then to make platforms that are open and accessible remotely. About the call for projects, so actually we had first call for project that ended recently, and we will have one other project that will reinforce this project 2 year on networks, and we will have also hopefully a project related to technology building blocks, but related specifically to photonics. And we intend to have one project related to economy and societal impacts on human science. But this one is not yet funded. Yeah, so about the general information, so about the leaders of the program, so there was decided by the government, there was 3 leading institutions. So one is CA, and I'm the representative CA leading this program. There is also CNRS, and Serge Verden actually is the leader for the program. And there is also IMT, leader is Daniel Kaufman. And so we were the 3 leaders shaping the program, but of course we work together with several laboratories and research institutions. So we have, of course, INRIA, but we have also other institutions, or many French universities and engineering schools. So the total budget of the program is 54 million euros. And so, as I said, we have several activities within this program. So we have targeted projects, we have platforms and demonstrators, we have call for projects. We have also a program in order to increase the maturity of the scientific ideas that coming from the project, from the different projects. So increase the maturity means that we want to move to technology readiness level, so TRL, up to 4. And we have also to hire a lot of PhDs, so 100, and also 70 postdocs. So the project started beginning of May last year, and the duration of the program is 6 years. So the first project, the 10th project, will end at the end of 2027, and the total end of the program is April 2029. So the goal is, of course, to consolidate a network of industrial and institutional around the program. So the funding is aiming at hiring this 100 doctoral PhDs, and this is going, and also for the investments. And but we have also 500 permanent scientists, which are not funded by the project, but who are contributing to the program. And for the time being, for the 10 ongoing projects, we have these 34 research laboratories that are involved in the programs. So you see that you have the representation of good representation of the different laboratories across France. So I'm from CEFIPRA-FUNDED, so I'm here actually. And we have. So this is from the university part, but we have also a goal to make collaboration with, let's say, institutional representative and industry. So we have links with other PEPR initiatives, for instance, electronics, or micro and nano electronics, and also cyber security. We have also links with the French National Space Agency, and we have also links with the Directorate General of Armaments, so the defense part. We have also discussions with regulation authorities, for instance, with the frequency regulation, and the ANSES, which is looking at the security for the health. We have also links, of course, with the Directorate General for Enterprise, DGE, and with the Ministry of Research. And we have links with the equipment manufacturers and operators in France. We have links, for instance, with Nokia, Ericsson, and Orange. And we are also linked with the Sector Strategic Committee, the Digital Infrastructures, we have brought links with them in order to structure the activities. So this CSF is including enterprise and operators and so on. And last but not least, we also try to set up collaboration with European and international research centers. So, for instance, for the time being, we have made some links with the NICT in Japan. And at the European level, we are discussing with the German hub for 6G. About the projects now. Here you have the 3 projects that are dealing with higher layer and security. And this is actually you have first one at the higher layer is the NF-MUST project, which deals with the 5G and beyond multi-domain services management architecture. So in this project, the objective is to provide structured automated code from service demands to service ordering. Second project here is NFNA, which deals with networks, architecture and infrastructures, and networks, cloud, and sensing convergence. In that case, the project is focusing on edge-to-cloud continuum, on end-to-end network slicing, and on AI-based operation control and optimization. And here on this part here, you have the project NFISEC, which deals with cybersecurity for future networks, which is focusing more on the security at, let's say, network layer. So the objective of this project here is to ensure a secure networks through management, to offer security services to users and operators, and to embed security and reliability in the network layer. Then you have the cluster of 3 projects that deals with technological building blocks. So I will not give details now on this project because I will go into more details afterwards. And then we have the let's say the end-to-end system level project. So on the left here you have the NFS project, which deals with IoT and industrial IoT. So there are 3 main parts on this project. Goal is to improve performance to serve applications for massive IoT, which are the most demanding for integration. This project also deals with specific needs for mission-critical applications, and in that case, the focus is to increase the robustness of the communication. And then there is the third part is dealing with resource sharing and interoperability for vehicular applications. And in that case, the goal is to focus on the most demanding part for data processing. Then you have this project here, NFGen, which deals with just enough networks. So in that case, the idea is to focus on sobriety. So about sobriety, the idea is to reduce the electromagnetic field exposure and also to reduce the energy consumption. Also to have a look at life cycle analysis and sustainability of the technology that are developed in the PEPR program. Another part is related to energy efficiency, for instance, on resource optimization, energy-aware orchestration and management. And the last part is related to context awareness communications, for instance, looking at backscattering communications, which means zero energy communications. And last but not least, we have the most theoretical project here, which is NF-FUNDED, which tries to identify the theoretical limits of implementations for network deployment. So this includes information theory, coding theory, semantic communications, and also stochastic geometry development. Now we'll make focus 3 projects which are dealing with the technological building blocks. So the first project I will talk about is Perseus, which stands for Power Efficient Radio Interface for sub-7 GHz distributed massive MIMO. So here you have the classical performance of network where you have large variation data rates that are witnesses through the cellular deployment with high peak at cell centers and low quality at the edge, and this is due mainly to the intercell interference and also to the handover management procedure. And the idea is to move to this traditional cellular architecture to another architecture which is based on cell-free, massive, multiple input, multiple output system, which consists in distributing an important number of access points over the deployment area, as you can see here. And these access points actually cooperate to serve the user equipment optimally by exploiting actually the massive micro diversity gain, because these access points are generally connected to a central processing unit via frontal links, as can be seen here. And by doing so, each user and serving the average distance between each UI, each user equipment and its serving access point is reduced compared to the classical cellular configuration, and shadowing effect is combated by the spatial diversity. So as you might have understood, the idea is to get more consistent quality of service over the distribution. So the scientific challenges and objectives of that are in this project. The first part is to increase the technology maturity of sub-7 GHz cell-free massive MIMO, and more specifically, the idea is to deal with realistic scenarios, which include real channel creation, and also to look at hardware impairments. And second part is to look at scaling up of cell-free massive MIMO solutions. So it includes physical layer and MAC layer solutions, but it also includes hardware developments, for instance, antennas and circuits. So the first work that was carried out within this project was to think about specific use cases and scenarios. So here you have three scenarios that were. First scenarios is looking at terabits experience data rate, so for ultra dense area. So in that case, of course, the idea is to expand network capacity and align with exponentially growing traffic demand, and it will result actually in a high number of it will result in high network densification in dense, as you can see here. So here you have a dense deployment with the access points in red here over a scientific campus here in the north of France. So that's fantastic. Another scenario here, which is tackled, is the smart factory scenario, where the idea is to monitor and control of digital twins related real-time processing by using this cell-free massive MIMO technology in order to provide extremely high reliability and low latency for a large number of massive devices. And the third scenario is related to vehicular communications in order to ensure consistent signal quality across all areas. So for vehicular to infrastructure deployment. Here you have an example of what was done actually for real case deployment in cell-free networks. And actually what was carried out was the vehicular to infrastructure channel measurements with a distributed MIMO channel sonder. So actually it was for the downlink and at the transmit part, the antennas are patches mounted in a horizontal linear array, and for the receiver part, so you have here the omnidirectional RX antennas that are put on the top of a van roof. And actually, what was looked at was a different configuration. I don't know if there's a problem because I saw something on the chat. Can you see my slide? I'm on slide 17?
Yes, we can see the slide on 17.
Okay, because there was a message on the chat. Okay. So here you have the different configurations that were looked at. So actually, there were 4 configurations, and one configuration is only with one access point here, with 8 antennas at the transmitter part. And then there was configuration 2 with blue with 2 access points, each with 4 antennas at access point, and so on, moving up to the 4th configuration with 8 access points, but with 1 antenna per access point. And this is actually, let's say, the most distributed antenna systems. And what you can see actually here, we plot the cumulative density function of the received SNR. And actually, you can see that when you increase the number, when you distribute the access points, even if you have only 1 antenna per access point, you can see that you achieve the best SNR condition at the receiver part, which means that you have a more consistent good service quality offered by this distributed MIMO system. So you have probability to get, here you have a probability to get 100, probability of 1 to achieve this at least 20 dB at the receiver with this configuration, whereas it's only 50% with 1 access point with antenna. Another things that was looked at actually was to look at stacked intelligent meta surfaces for multi-user. So actually, the idea is to use reconfigurable intelligent surfaces, but instead of looking at only one single layer meta surface, the idea here is to stack several several layers of meta surfaces in order to achieve a good multi-user interference suppression. And actually, with this kind of solution that is looked at by actually Marco Di Renzo at Supelec, and I think that you will have a presentation. I don't know if it's today or tomorrow on this specific topic. So here, basically, the idea is to perform transmit beamforming directly in the electromagnetic wave domain. And actually, as a result, with this solution, you can overcome the need for digital beamforming, and you can also lower the number of you can operate with low resolution for digital to analog converter. And what you can see here is that when you increase the number of meta surface layers, you can see that you increase the performance of the sum rate, and which means that you suppress the multi-user interference, and also at the same time that you can see is that we get a very good performance compared to, let's say, a more classical solutions. Another study that was carried out in this project is to look at pre-coding for a cell-free massive MIMO. As I said previously, the idea is with this cell-free massive MIMO system is to use, so to have a high number of access points, but to have also at the same time low-cost hardware actually. And when you bring low-cost hardware, you have more hardware impairments. For instance, you have more sensitivity to let's say to a PEPR degradation. And what was done here is to look at this PEPR pre-coding distortion in order to use a low-cost radio, but at the same time to have very good performance. So here the algorithm consists in a novel downlink transmission scheme that can anticipate the PA-related distortion by adding frequency domain peak cancelling signals to the transmitted one. And actually this is what can be seen here with this solution. For the downlink again, you can see a 40% spectral efficiency gain with the solution at an input backoff of 3 dB. So this is this point here. And you can see also that we have 30% energy efficiency gain compared to a classical solution that do not take into account PEPR pre-distortion. Another algorithm that was developed here is to combine actually a reconfigurable intelligent surface with non-orthogonal multiple access, and this was proposed by IMT Atlanta. I think also that there will be kind of presentation on this later details on that, but the idea was to combine actually this RIS reconfigurable intelligent surface plus this non-orthogonal multiple access scheme, and this is done basically with 3 steps. The optimization. So the first step is using multi-arm bandit for subband allocation. Then you have a RIS configuration for received power level attribution, and then you have a RIS selection using the branch unbounding algorithm. And what you can see actually is that you can double the total achieve rate compared to a more classical solution. So you can double the achieve rate compared to orthogonal multiple access scheme, and you have an increase of 30% compared to NOMA without this RIS usage. Now about the Yakari project. So this project is looking at millimeter wave frequency, so ranging from gigahertz up to 90 gigahertz. So there are several studies projects. So one study is related to advanced millimeter wave circuits and subsystems. So this includes actually millimeter wave RFIC development and also high power amplifier design and integration. One other topic is related to new active antennas and RIS concept at this millimeter wave frequencies. And one other part is related to dedicated signal processing. So this includes RIS processing, this includes beamforming, but it also includes radio functionalization. For instance, to make at the same time communication and sensing. So this is joint communication and sensing solution. So for the antennas part, so here you have one hardware solution that is developed, which is a reconfigurable intelligent surface. And what is done actually is to make a reconfiguration of the lens that is here. So in this system, you have a source that is illuminating a lens, and the lens is here. And for the steering logic, actually, we use a pin diode in order to make the phase modulation. And with that, we are able to make the reconfiguration. Sorry. But of course, as you can see, it's quite volume. There is, let's say, high volume occupancy due to the focal distance that is here, depending on the performance and the wavelengths. And we are working on designing low-profile solutions, for instance, by increasing the number of sources. And about joint communication and sensing, actually we are working so that when you are doing joint communication and sensing, there are some issues. You have, for instance, to work on self-interference cancellation, because at the same time you transmit, you try to receive the reflections coming from outside, which means that you need to make a kind of self-interference cancellation mechanisms. So this is what we are aiming about full duplex front-end modules. But this is for the RF part, but you have also to make some signal processing because you have at the same time communication signal, but also radar processing. So here you have an example of what was achieved at 26 gigahertz. So we are using a radio working at 26 gigahertz with 200 megahertz bandwidth, and we test transmit and with OFDM signal. And what you can see actually here are the obstacles that we put on the ROM. And you can see that with this front end, we are able to to see the two obstacles. So this is the first, let's say, simple proof of concept that we did with this joint communication and sensing process. And now about Sistera project. Now we move to even higher frequency. So moving up to beyond 90 gigahertz. And in that case, actually, are several objectives and goals. So first is related to architectures and waveforms towards very high frequency and very high throughput systems. Another thing is to look at propagation of very high frequency waves. So we have channel measurements. Another part is related to D-band and H-band system implementation. In particular, looking at amplification of the signal and frequency synthesis. And then we also intend to make demonstration of this band's potential by making the assembly of developed bricks. And here you have an example actually of what was done at 300 gigahertz. So the idea was to make a validation of a wireless communication link in the sub-terahertz and using a photonic-based transmitter and a waveguide fed micro-machined wideband flat antenna. And here you have the flat antenna with 1000. This antenna was presented at the European Microwave Conference. And here you have the measurements that were carried out to characterize the gain of the antenna. So we achieved a 36 dBi gain over the whole range, the frequency range for communication. So ranging from 320 gigahertz and 400 gigahertz. And here you have the performance on the voltage bed, so including the modulation and transmission. So what was done here was the usage of 16 QM modulation, and with that, with these 5 channels here, we were able to achieve a total bit rate of 300 gigahertz, 300 gigabit per second, 300 gigabit per second bit rate, which is very huge at this frequency. And lastly, I will end with a few words on our platforms and demonstration that are in the project. So actually we have 3 platforms that are developed in the project. One platform is related to RF frequency tests facilities. So this includes components and hardware subsystem characterization, and this is led by Philippe Benieff. And there is one other platform which is looking at a deployment of beyond 5G network infrastructures, and this platform is led by Raymond Knop from Recom. And there is also another platform which is led by Philippe Martins from Telecom Paris, which deals with next generation cellular and for AI and IoT. And I think that this platform will be explained will be presented during the workshop later by Philippe. So with that, I would like to thank you for your attention.
Long live India and France friendship.